You of where we were yesterday. Yesterday we started a brand new topic. What were we talking about?
Forces.
Forces. Yeah, we're talking about forces, and we know. What do we remember about forces? There were two big things that are true of all forces. Remember what they are? The very beginning. Two big things. They're a what? It's a push or a pull. And it's always an interaction between two objects. That two objects thing is so important. So I'm going to keep saying it over and over and over because it's super important. We also focused yesterday on two specific kinds of forces, right? One of those was what? Commonly known as gravity. We know that instead of calling it gravity, most of the time we're going to call it the force of the earth on the object. Awesome. And then the other one had a really strange name. We did this on the very end. The normal force. Normal does not mean regular, plain old, or unexciting. It really actually means perpendicular. I love it. You guys have got this. Fantastic. All right. So yesterday we started, oops, you can't see that. Yesterday we started this problem. We started talking about weight, which again is that force due to gravity, due to the earth. The normal force is that perpendicular force. And we found the weight of the box, didn't we? Do you remember that? Do you remember how we calculated that? Or you're looking at your notes and so you can write it down. Yep. The force of gravity. What was the formula or the equation that we used to find the force of the earth on an object? M times G, right? M is the mass of the object. G is the acceleration of the earth, or the acceleration of the object as the earth pulls on it. G has a value of negative 9.81 meters per second squared. We multiplied our 10 kilograms times negative 9.81 meters per second squared. We can do that in our heads without even thinking. We've got what? How much force? How much is the earth pulling on the box? Multiply by 10. What is it? 98. Ah, look at that. Newtons, right? That terrible, evil, very smart, but not very kind individual. Isaac Newton gets the name for that, okay? So we got negative 98.1. The negative sign means what? That it's going down. Awesome. We're rocking it. All right. And then we did the normal force, Fn. And did we have a formula for that? We didn't. We kind of glossed over this because I really wanted to get it written down yesterday before the bell rang. But I want to make sure this makes sense. So I'm going to draw my box. And I'm going to have you do this too because this is for part A. And then we're going to do parts B and C right now after we do part A. There's my box with the mystery whatever in it. Please draw a free body diagram. Free body diagram of that box. So a friendly reminder that a free body diagram is the box and all of the forces acting on the box. So you can look back to the picture of the frog that we drew yesterday, if that's helpful. It is absolutely fine, ladies and gentlemen, if you want to talk to each other, if you're not sure what to do, you want to confirm with your neighbors. How many arrows are you drawing? 2. One goes down, the other one goes up. The one pointed down is the force of the earth on the box. And in parentheses, I'm going to write FG just to remind myself, oh yeah, that is that gravity thing that we're talking about. But when you label it, I want you to label the force of the earth on the box. Okay? And then we've got another force. What is that? The table. Those arrows should be about the same size. On an AP exam, the readers do not get rulers out to measure. But if you have one arrow that's pointing down and the other one that's pointing up is like that they will count it wrong, which is kind of sad. We don't want that for you, right? We want success. We want happiness. So we're just going to make sure that we draw it about the same length because we know that they're about the same length. And that's the force of the, what did you say? Table on the box. In parentheses, I'm going to remind myself that that's a normal force. Normal means that it's perpendicular to a surface. It's a surface force that's acting. Now, we said yesterday that we knew what Fn was, but we didn't really talk about how to calculate it. How can you find the normal force in this case? It's the same as the force due to gravity, right? Because we know that they have to add up to 0. So we can say, we can reason through that the box is not moving, which means that the net force has to be equal to 0. You with me there? Adding them all up, they have to be equal to 0 because it's not going anywhere. That's really the force of gravity plus the normal force. If the force of gravity is negative 98.1, the normal force then probably should be 98.1, right? Newtons. Yeah. So that's how we figure out the normal force. There is not an equation, a formula for the normal force. The reason for that is that it changes. Oops, 98.1. Try to write that more accurately. There we go. Speaking of it changing, let's take a look at part B. Before we do that, everybody cool with what I've written down so far? Okay. Part B says, now, for some reason, your friend is going to push down on the box with a force of 40 newtons, as in the picture that doesn't exist, so we'll draw it, okay? The question says to again determine the normal force exerted on the box by the table. Okay? So we're not going to draw the picture, or we don't have the picture. We're just going to use our picture that we already have. So we've got the earth pulling down on the box. We've got the normal force, and now we've got somebody else, right? Which way's that arrow going to go? It's going to go down. It said that your friend is pushing down. I don't know why. It doesn't make a lot of sense. But for some reason, your friend is pushing down on the box. Now, that arrow is not going to be quite as big, is it? Because it's like 40 newtons. But this is the force of your friend on the box. Generally, if they talk about a person pushing or pulling, I call that an applied force. So I'm going to put a little parentheses F sub A in there for applied. Your intuition might tell you what that normal force should be, but I want to think it through. Is the box moving in this case? It's not moving, which means that the net force acting on it still needs to add up to what?
0.
0. So we're going to write that down again. So here we go. I'm going to do this in a... This one was for A. This one is for B. Here it comes. So F net is going to equal 0 because that box isn't going anywhere. Just going to add them up. So we've got FG, we've got FA, and we've got FN. Now it may be helpful to pay pretty careful attention to directions here, right? FG and FA are going in the same direction. You with me there? So we can solve this for FN. We know FG is negative 98.1 newtons. What is FA? Say 40. Friend pushes down on the box with 40 newtons. So that's going to be a negative 40, right? Plus Fn has to equal 0. What does Fn have to be then? Negative 98 plus negative 40 is going to be negative 138.1 newtons plus Fn equals 0. Okay? Normal force is really, really funny. Because the normal force, the force of the table, varies depending on what else is going on. It's weird. Let me tell you what I mean. If I put a Kleenex that weighs just a couple of grams, right? So the force of gravity on it is very small, and I put that on the table only has to push up just a little tiny bit. Are you with me there? Then I'm going to put something much larger with a larger force of gravity on the table. I'm going to switch it out. When I do that, what happens to the normal force? It increases, right? It's kind of like magic. It's not really, though. It's just physics. It's not magic. It's just physics. How does it work? Do you guys know? The molecules of the table are kind of like little springs. I don't know if you've ever seen one of those. They used to have them on TV. I don't watch TV with commercials anymore, so I don't know. Like commercials where you like see a mattress with like a bowling ball sitting in the middle, or like somebody like a kid like running across it with like a glass of grape juice that might or might not spill. Do you know what I'm talking about? Okay, so you've got like this mattress that kind of like gives when you put something on it. That process with the springs that push down is exactly the same process of what's happening here on the table. The table looks hard, and it doesn't look like it gives, but it definitely does. A little tiny bit. Okay. If I added bottle of Purell after bottle of Purell, and I just kept stacking them up forever, I moved the ceiling and just kept stacking them up forever, eventually, that normal force that keeps getting bigger and bigger and bigger, eventually it's going to break. Right? You with me there? Okay. Eventually, we're going to overcome the force that this can push up. But until then, that normal force is going to push up with just the right amount of force so that that object does not accelerate. It just sits right there. Okay. I know. I just caught myself. Good call. I did just say the A word, and I didn't mean to. Strike that from the record. Okay. Another way to think about that, I just promised that I wasn't going to use it before and then lied. Lies. Another way to think about it, this came to me, I don't know, a couple of years ago while I was doing dishes at my house, thinking about the normal force, because a lot of times we think about the fact that the normal force should be exactly the same all the time. If you have ever had the opportunity to clean dishes, take dishes out of the dishwasher to put them away, I don't know if your parents have ever given you that opportunity, but if they haven't, ask for that opportunity sometime because it's really fun. But maybe get somebody to help you. If you imagine, so I want you to imagine, if you just have your hands out, okay, somebody puts a plate on your hands. The normal force, or your hands pushing up, is going to be exactly equal to the gravitational force pulling down on that plate. You with me? Okay? Somebody, your parent, your sibling, your cousin, whatever, puts another plate on top of it. What happens to your force? It has to go up a little bit, right? You may not even notice it until they start stacking like 6 or 7 plates, and then eventually you're like, oh, hello, right? You realize that you're pushing up a lot harder than you were with that first plate. Okay? That force, that change, is the same as what happens in a surface. Okay? It's not conscious. I'm not trying to anthropomorphize our table. Okay? But that change has to do with how much is being pushed down. Important to know. All right. Part C. Your friend is goofy. I don't know. Here's a present. Let me push down on it. Now I'm going to take it by the really fancy bow that I put on the top, and I'm going to pull upward on the box with a force of 40 newtons. I don't know why. I don't know. Maybe they like physics. They want to just try it out, right? Okay. When they pull up with a force of 40 newtons, is the box going to go anywhere? Ooh, let's find out. I'm going to draw the picture down here again. Here we go. So here's my pretty picture, or my pretty box. Maybe if my stylus will work. There we go. With my kitties or my M&Ms or my whatever's in there. I'm going to put a little fancy bow on it. So there's the pretty bow. So tell me about the forces that are acting here. What have you got? Force of the earth on the box. Where does that go? Down. FG. Boom. What else we got? What'd you say? Force of the table on the box. Which way is that going to go? Up, because the table is horizontal. The normal force is going to go perpendicular, so it's going to go up. That's an FN. You with me here? How we're labeling this? So we're saying object on object, and then we're putting the type of force in parentheses. Okay. And then you've got your silly friend. Your silly friend is pulling up. The force of the friend on the box. F applied. A is applied. Well, that's what we need to figure out, right? It's smaller than this one. We don't know about this. Let's write down our F net equation. F net. The forces that are acting, we've got FG, we've got FA, and we've got FN. What's FG? Say it again. Force the earth on the object. How big was it? Negative 98.1. How big is the applied force? 40. Is it positive or negative this time? Positive, because it's going up. So now I've got 98.1 going down, 40 going up. Is the table still pushing? Yes. It's got to be. Because if it wasn't, then this thing has got a bigger force going down. That doesn't make any sense. So we got to have some sort of normal force acting. If the normal force is acting, then we're probably not accelerating. I said it again. Jeez. That's embarrassing. All right. How big is the normal force going to be this time? 58.1. Three situations, same box, same friend. 3 different normal force sizes. That's kind of weird. 98.1 going down, or excuse me, going up. 138 going up. 58 going up. How are we doing? Are we okay so far? Is that a yes? No? Yeah? Yeah? Okay. I couldn't quite tell. All right. Let's do another one. We'll get it set up. We probably won't make it all the way through it today. We'll give it a shot. So now your goofy friend, the one that's pushing on the box and pulling on the box, maybe it's not the same one that asked about the box, or they gave you the box. Because now it says that the friend asks to examine the box. I want to know what's in it too. Shake, shake, shake. I hope it's not kids. Okay? Hoping to guess what's inside, you say, sure, pull it over to you. She pulls it over by an attached cord. That was a detail that we left out before. Who knew? There's a cord on the box, as shown in the picture we're going to draw, pulling along a rough surface. Oh, that's interesting. The force exerted by the person is 40 newtons. It's exerted at an angle. Oh, man. That's great. We got it. Calculate the what? The what? We got it right. Let's draw a picture. Too much in there for me to think about. Draw a picture. You draw a picture. Draw a picture of your box. Draw a picture of your box. Be good time to start your page if you're like partway through a page. I know. Draw a picture first. We won't get the problem done today. We can certainly draw a picture today. How many forces do you have? It's a good question, Ms. Carmeling. I don't know. Friction. We haven't talked about that yet, have we? Something for tomorrow. It's going to be great. The day or before the bell rings. We'll do this tomorrow. I do want to remind you that I am going to talk about homework tomorrow, so I do want you to go through these 3 problems. Chapter 4, problem number 7. Chapter 5, questions number 10 and 17. Okay? First one's a problem, the second 2 are questions. Sound good?